Okay, let's get started. So in this video, I'm gonna go over the concept of ASM charts. You will see this is just a alternative representation of finite state machines. Okay, and then I will cover VHDL for state machines, which is something very important that you need to know for, especially for your lab number 6 and final project. Right. So let's try to cover first the ASM charts. Well, as you have seen in the examples here, for the most part, we use what we call the bubble representation. So for FSM representation, I guess for lack of a better name, we call it the bubble representation. And if you remember, it requires, to specify inputs, then slash output, right, in the diagram. And well, if we have, let's say, one input, then we can have two arrows coming out of each state. Okay, like in this case, for example, let me show you here. We only have one input and one input X here, and we have, say, 1 and 2 arrows from each state. What if we had two inputs instead? Let me show you. One input, then 2 arrows out of each state. And we can do the same for this. 2 inputs, then we have 4 arrows out of each state. What else? What if we had 3 inputs? Now you have 8 arrows out of each state. You will see that a normal state machine can have many inputs, 5, 6, 10 inputs. So I would say that the bubble representation is a very convoluted representation, not actually very useful for real state machines. So to save the day, what we have is actually something called algorithmic state machine charts. It's called ASM charts. It is a slightly simpler representation. It might not look to you like that for simple examples, but we will see that in unit number 7, using ASMs will be almost mandatory because there is not really other way to do this. Okay, so let me try to cover this. Okay, it's actually pretty simple, but there are some small details that you should always keep in mind. So you have, of course, this in your notes. First, take a look how all the state machines are actually here in the bubble form. Here we have the topic of algorithmic state machines. So, for example, this right here, state machine, which is a gray counter, actually you could represent that by this state machine. This is the ASM chart. This box and rhomboid here, right? On its surface, you can say that this representation, ASM, looks more complicated than this one. And I would agree. For really, really small state machines, actually the bubble representation is a very compact representation. Okay? But this representation will be much more efficient when we have to deal with very large state machines. Okay, so let me try to do one example. Let me see. If you remember your example of your counter, this is the counter for 0, sorry, the example of the sequence detector for 0, 1, 1, 0, 1. Oh, well, I guess there's a small mistake there. Let me try to do it this way instead. Sequence detector 0, 1, 1, 0, 1. Okay? So, and you remember this is our state machine. How can we represent that in ASM form? Well, let's try to do this. Well, the first thing you have to understand is the following, that a state is represented by a box. On top of the box, we write down the label of the state. For example, here, for state number 1, right, for state number 1, that could be represented like this, like a box with S1 on it. Okay? And of course, we have the reset equal to 0. Here, we indicate it in this way. Okay? Pretty simple. Okay, this is how you represent one state. So that's pretty easy. That's not usually a big deal. What else? So notice here that, for example, in number 2, I think, yeah. In number 2, let's say, well, number 3 if you want to. In number 3, we have two decisions, right? Whether to go to state number 2 or to state number 4. This is determined by whether the input is 1 or 0. So it's kind of, we're sort of as if we're having an if statement. So that can be easily be represented by a rhomboid. Okay, by a rhomboid. Okay, let's continue. Like I was saying, this is the sequence detector for 0, 1, 1, 0, 1, and this is the normal state machine method, right? This is the bubble form, if you like. Okay. And well, the state is represented by a box in this case. Okay, and whenever we have to make a decision, for example, of whether to, for example, go from state 2 to state 3 or to remain in state 2, that depends on the input usually. Okay, so that depends on the input, and that is represented by a rhomboid here. Okay, x is value, if the value is 1, we go to a certain state, and if the value is 0, we go to another state. That is as far as this representation goes. There is one more box, and I think I will cover it soon, but this box is like a rounded rectangle. Look at it. Okay, and it will be used to represent outputs. We will see in a moment how that's gonna work. Okay, so for now, let's just focus on the state transitions, and that should be pretty easy to do. Let's take a look. So we start on state number 1. Okay, and then if the input x is equal to 0, we move to state 2. If the input x is equal to 1, we remain in state number 1. Well, that should be pretty easy to do. All we have to do is to include this rhomboid right there. So if x is 0, we move to state 2, because this has to change. And if x is 1, we go back to state 1. So that's all that we have to do here. And of course, once x is 0, we of course do move to state number 2. That is the second state. And in number 2, we have to ask a question. If the input is 1, we move to state 3. If the input is 0, we remain in state number 2. So we have to use the same rhomboid here and ask the same question. There you go. But now, if the input is 1, I am going to move to state number 3. If the input is 0, I am going to remain in state number 2. Okay? And I go, of course, to state number 3 now, when x is 1. Okay, that should be easy, right? In state number 3, what happens? If the input is 1, we go to state 4. If the input is 0, we go to state 2. So we have to, I guess, copy this and put it right here. So if the input x is equal to 0, we go back to state 2. Oh, we have to do it this way now. This arrow goes back all the way here. There. If the input is 0. If the input is 1, though, we have to go to state number 4. So we'll do it here. Now we have state number 4. And in state number 4, what happens? Well, kind of the same thing, right? We actually are going to ask ourselves whether x is equal to 1 or 0. If x is 1, look at this. It will go to state number 1. If x is 0, I move on to state number 5. Okay, so let's do that then. So if x is equal to 0, what happens? We move to state number 5. See here. But if x is equal to 1, we move to state number 1, actually. So we go all the way here to state number 1. There. Okay. Now, when we're in state number 4, of course, if x is 0, we move to state number 5. So we are here, and we do this. And that would be state number 5. So again, in number 5, if x is equal to 1, we move to state 1. But if x is equal to 0, we move to state number 2. So we ask ourselves the same question, and this is what we have. If x is equal to 1, we move to state 1. So we are right here. Right, sort of the same arrow here. What happens when x is equal to 0? Oh, according to that, we have to move now to state number 2. So if x is equal to 0, we now move to state number 2. There. And there you go. This is how you actually show the transitions, right? Okay, so that's how you completed the transitions between states. And yes, I mean, for now, of course, it will look as if this ASM form is a bit more complicated than this. It is just because of the simplicity of this state machine. Okay, what else? Well, we have so far indicated what happens here to the input. Sorry, when the inputs change. We have not indicated what happens to the outputs. Well, let's take a look. In state number 1, what happens to the outputs? If the input is 0, the output is 0. If the input is 1, the output is 0. So notice that in state number 1, right, in state number 1, the output is always 0. So let me try to type it up here. For the sequence detector 01101, for state number 1, the output C is always 0. And the same for state number 2, same for state number 3, Same for state number 4. I guess the difference comes when we're in number 5, right? Z is actually kind of X, right? This is why this machine is milli, right? It's a milli state machine. So let's try to do this now. So we know that if we're in state 1 all the way to 4, the output Z will be 0. What about S5? We can put it this way. If X is equal to 0, then Z is equal to 0. Also, if X is equal to 1, then Z is equal to 1. Okay. That's a better way to put it. I will tell you why in a moment. So let's try to do that then. So, number 1, how do we indicate that Z is equal to 0? Well, like I said, the output is indicated right here with a rounded rectangle. So we can say here Z is actually equal to 0. Just a moment here. There you go. You use an arrow, Z equal to 0. There you go. So you can put it right here, right? When X is equal to 1, of course, Z is going to be 0. Okay? Just a moment here. Yeah, there. Okay. So, let me show you very quickly how this is going to work. Okay. So, what I would do is I would indicate like this. I would put this rectangle here. Sorry, this rounded rectangle here. Such that if X is equal to 1, then Z is equal to 0. And I would do the same thing for the remaining portion. Let me be more clear here. It should look like this actually. And also, if X is equal to 0, you also do Z equal to 0 here. Okay, so that's how you would usually indicate it, okay, for X. Now, let's be clear here. Z equal to 0, of course, happens regardless of the value of X. So, a better way to denote this is by just writing this Z equal to 0 on the state box. Because we know that Z will be 0 on state 1 no matter what. There you go. If we do that, we can just get rid of this box and this other box right here. So that's a better way to indicate, right, that Z is 0. Okay, I hope that's clear. That's one way to do it. Now, the same thing is going to happen to state number 2, right? It will be the same in state number 3, state number 4. Oops. So what about state number 5? That's a bit different, right? Because remember, if X is equal to 1, the output is 1. But if X is equal to 0, the output is 0. Oh well, now we cannot do this anymore. Because the value of Z depends on now not just the value of the state S5, but also on the value of the input X. So in this case, I can say that C equal to 0, that's incorrect now, right? Okay, so we have to get rid of that. Okay, so how would we indicate that? Well, if X is equal to 1, then Z is equal to 1. And if X is equal to 0, then Z is equal to 0. There you go. That's how you would indicate it. Okay, that's why we use this rounded rectangle for to indicate what happens, right? If Z is equal to 1, Z is equal to 1 only when X is equal to 1 and state is number 5. Notice, like I said, that this is a milli state machine. Why? Again, let me repeat myself, because the output Z depends on the state S5 and on the value of the input. Again, how can we remember that? Well, you have to go to this picture that I asked you to remember. The output here is Z, and it only depends on what? On the present state right here and on the input. Okay, that's why it is milli. Okay, I hope that's clear. So now, before so that should be all. That should be all. However, here is one feature of the ASM form that you might find odd, but it is actually going to be very useful later. So what happens is the following. In the ASMs, let me put this here. What happens in the ASM charts? Well, first of all, state is indicated by a box. A decision is a rhomboid, and then another thing, and this point is well, I would say it's optional, but it's almost mandatory. For outputs, only indicate the cases when the output is 1. What does that mean? Well, and this is going to sound very weird. It means that when no output value is indicated, it is assumed that the value is 0. Okay? This is, let me repeat myself, optional, but strongly recommended. And you will see that this actually will be very useful, okay? Because when we have to deal with large state machines, you don't want to indicate all the values of the outputs. You will see that only using the values that are 1 are the ones that are is what makes sense. Okay. Again, it's optional, which means that you can still indicate cases when the output value is 0. There is nothing wrong if you do it. But I am just letting you know that if you see a state machine, an ASM, for which you don't see a value for the output, you have to assume that it is 0. So you can still indicate these cases when the output value is 0, of course. And people still do it. Sometimes I do it myself too. Usually done for emphasis, to emphasize to make a particular point. Okay. But for the most part, you don't. So then what does it mean for our picture? It means that there is no reason to indicate this, or this, or this, or this, or even this rounded box can be done as well. So, okay. So this state machine right here, I mean, I wouldn't say it is incorrect, but it is uncommon. It is much better to actually represent it this way. Okay, this is I'm gonna say this is a more compact representation. Okay, please remember this point. Okay, we will see that a lot later. this compact representation will be extremely useful when you have to design large state machines. Okay, so ASMs, like I said, very useful to represent large state machines. With many inputs and outputs. Not only that, and this is my next point, and this is what I'm going to do in a moment, it will map very well to VHDL. We will see that in a moment. Okay, so that's the point I wanted to make. Please remember this. Okay, it will be very important. Okay, so now let's go on to the next topic that I wanted to talk about, and this is what we know VHDL for state machines. Okay, this you can find, of course, in the Unit 6 of the tutorial. Let me quickly go over it, and then I will go over an example. First thing to mention is that when you do VHDL coding of anything, for that matter, but especially of state machines, right? Let's see, FSMs in VHDL. There are many styles. If you go online, you will find, of course, a bunch of styles. That's the first thing you gotta notice. But in this class, I teach a particular style that maps very well to the FSM, the state machine model. Remember that picture that I showed you? This picture right here. Okay. Let me try to start. Well, the first thing you gotta do, and you will see that this is actually very useful, we have to let's talk about the style in this class. So the FSM coding style in this class. So first you have to define a proper variable, and the variable is going to be type state. And then you define all the states. For example, if we had 5 states, we do S1, S2, S3, S4, S5. This is how you define a new data type. Okay, and this state is just by the way, a label. You could have called it whatever you like. You could have used stat or STA or ST. Doesn't matter. Okay. I'm calling it state because I guess it's simpler, right? It's more natural. Now, what about the actual signal, right? Remember this? The actual signal right here. This signal Q. These bits. But now we're going to represent that using a label as opposed to actual bits. Well, we have to define a signal, right, of type state. Okay, in that case, this signal Y, that's how I prefer to use it. You can call it whatever you want. Y can be what? S1, S2, S3, S4, S5. Notice that this state right here, these labels can be anything you want. I could have used easily SA, SB, SC, SV, SC. Okay, whatever you want. I'm using here S1, S2, S3. They don't even have to start by an S. You could have used T1, right? T2, you name it. It's whatever you want, okay? Okay, once you defined those, this against new signal, right, you have to now use two processes. Remember the processes? Now you use two. The first process is called a transitions process. This is how we call it, by the way. It's just a name that I'm using for lack of a better name. This will indicate how we switch from one state to another based on the input. And the other state is the, well, what I call, of course, for lack of a better name, the output state. The output transition, sorry. The output, sorry, process, which is to indicate how the output values change based on the present state, of course, and the input, if it is a milli state machine. Okay, so we use two processes, and here is what I wanted to tell you. This is going to be very important. Remember this figure right here. So, well, the first process, the transition process, will represent actually this block, this combinational block, and this flip-flop, while the second process, right, is only this combinational block here. So this output process, we can say that this is a combinational circuit only. Sometimes they call it a asynchronous process, asynchronous process. And here, the transition, this is actually a synchronous circuit, right? Or also a synchronous process. Okay, keep that in mind, please. Okay, we have two processes. So now, let's take a look. So this process, we have inputs, right? And the output of that process would be what? It would be the state. And remember, what is this? That is the present state. So we will get the present state. We will use the present state, right? And the inputs to determine what? The next state. Remember, this is right here. Is the what we call the next state. Okay? And this Q right here is the present state. Okay, we have the present and the next state defined by the transition process. Okay, this process has what? Two inputs, right? Please pay attention carefully here. This process has two inputs. What? The actual inputs of the state machine and the present state. Okay, and it only has one output, which is the value of the present state, but on the next clock cycle. Okay, we will see this slowly, okay, in a moment. What about this output process? Oh, it's actually pretty easy, because look, what are the inputs to this output process? Only the present state and the actual inputs, and the output is just the outputs. Okay, so please keep this in mind. This picture actually will be very helpful, okay, even for VHDL. So let's take a look at how you would do it. Well, right here. So let me show you one example then. Let's forget about this example, you can look at it later, but let's focus on the example like this, for example, sequence detector. Okay, for now. I'm gonna go very fast on this, but after that I am gonna actually show you how to do it in VHDL for the sequence detector we've been talking about for this state machine. Okay, so let's take a look. Again, how do we write the VHDL code for this, we have two processes, right? The synchronous process, the transitions, and the outputs. Let's look at the transitions. Again, this is the detector. It's a different sequence detector, right? 11010, and this is the ASM chart. Let's look at the code. Well, entity is the same, right? Clock, reset, and the input X, of course, and the output is only Z. What do we do first? We define the type state, and we use 5 states because that's what we need here. Only 5 of them. What else? We have the signal state. Easy. So what do we do? Remember, sort of like in a register or flip-flop, the first process, the transitions process, the inputs are, of course, reset, clock, and X, if you like. We will see in a moment, of course, and I told you already, that we will also use the present state, right, as an input in this process, even though it is not included right here. Even though it is not included explicitly there, but we will see. Okay. So first, what do? Well, if reset is 0, right, because this is asynchronous, what has to happen? Well, if reset is 0, I have to go to state 1. There you go, state 1. That's easy. What happens if reset is not 0? All we have to check whether there is a clock tick. And if there's a clock tick, what happens? Well, what happens is that the circuit, this state machine, is going to work now. What does it mean that it's going to work? That depending on the value of X and on the value of the state, we will move to a particular state. Let's see. For example, here, if X is 1, right, we move to state number 2. And you can see this here. If X is 1, we move to state number 2. If X is 0, we remain in state number 1. That's what you have here. That's all that line. And the same for state 2, 3, 4, and 5. So that whole thing was actually the first process. That process, as I was telling you a moment ago, all you do is to indicate how to switch from one state to another. Okay? So that is the first process. And that process is only this block here, this transitions process. That's what you did right there. You just indicated what would be the next state, right? Based on the present state and the inputs. That's all you have done there. Now, what about the output process? The one right here. So that will be another process. And in theory, it is actually very simple, but in my experience, many students actually make a lot of mistakes at this stage. Let's take a look. So again, this is the state machine. Notice what happens, right? Z is 0, remember, most of the time, except at this point when we're on state 5 and X is 1. Well, let's do that. So we have this here, this process that depends on X and Y, which is that's the present state. And what do? Well, we make first Z equal to 0. And once we do that, if you remember from the previous lectures, what happens? We only need to indicate now what happens when Z is 1. Because guess what? What do you think happens when a state is 1? There is nothing here. Who will take over? Z equal to 0. Right? What happens when X is 0? What happens? Who will take over? Well, this. Okay? This is why I was telling you that this ASM representation, actually maps very well to the not only to the FSM model, it also works very well with the ASM chart. Okay, almost natural. Okay, and that's all. That's all that you need to do. Okay, for that example. So now let me work on the example from here, right? And let me do it in Vivado. Okay. So I hope you can see this. I hope this is But just in case, just give me a moment here. Okay, here we go. So let's take a look at this example, right? This state machine, the one that I was working a moment ago, 01101. Let's try to implement that state machine. It's one step at a time. So let me see. I think I can do this. Yes. There you go. So what are the inputs of this state machine? Like I said, we have clock and reset. Those are obvious. E and X. We don't have an E. We only have X here. The input X and the output Z. What about the type state? We have, well, in this case, we are using S1 to S5. So we have S1, S2, S3, S4, and S5. The variable state. So the first process, remember, is just the process to transition between states. So at the beginning, of course, if reset is 0, because that's an active low asynchronous reset, what happens? We go to state 1. And then, if reset is not 0, we ask, is there a rising edge? Well, if that is the case, we have to, of course, first ask in which state we are in. If we are in state 1, well, we have to ask then what happens to the value of x, right? If x is 1, what happens here? We go to state 1, right? There you go. If x is 0, we go to state number 2, right? That's what you have right here. What happens when we're in state 2? Well, if x is 1, we go to state 3, actually. But if x is 0, we remain in state number 2. There you go. Now, in state number 3, if x is 1, we move into state number 4. Otherwise, we now go back to state number 2, actually, right? Or state number 3. Number 4. If x is 1, we go to state number 1. And then otherwise, we go to state number 5. Finally, in state number 5, what happens in state number 5? If x is 1, we go to state 1. And if x is 0, we go to state 2. You see? That's it. Okay, that's all you have to do for that part. The second part is the output, and that's a bit more, you have to pay more attention. I mean, it's actually easy, but I've noticed again in the past that this is where students make a lot of mistakes. Let's first do it, I guess, in the most, I guess, straightforward way, where we have, of course, all the 5 steps, right? How do we do it? Well, in state 1, what happens? Z is 0, right? Easy. In state 2, what happens? Z is also 0, because that's what we know from the representation right here. In state 3, what happens? In state 3, also Z happens to be 0. In state 4, also Z happens to be 0. Finally, in state number 5, that's where we get to ask the following. If x is equal to 1, then Z is equal to 1. Otherwise, what happens? Well, Z becomes 0. There you go. So that is one way to write this down. Okay? I mean, if you were to do that, you will be fine. There is nothing wrong with doing that. However, you will notice that when you have a lot of outputs, doing this, indicating all the values of the outputs for every possible combination of states and inputs will be actually very, very complex. It will take a lot of your time. A better way to do it is the following. We're going to just indicate what happens when z is equal to 1. Okay, but of course this is incomplete because this is wrong by definition. We need to make sure that at the beginning, remember how the process works? We have to make it 0. This is what we call default value. Okay. This means that in state 1, z is 0. This also means that in state 5, if x is equal to 0, so if x is equal to 0, if x is equal to 0 here, we take z equal to 0 as well. Okay, that's what it means. Let me just mention very quickly a very common mistake is to omit the default values. You will be creating what we call a latch, and that's not what we want, because remember, this process is a purely combinational circuit, right? Remember this picture here? This output process is a purely combinational circuit, so please do not make that mistake. Most of the mistakes that I see in lab number 6, or even in the homework 4, or even the final exam, is because students forget about these default values. Okay, so please don't forget that. This is a very common mistake, by the way. It might look very simple now, I mean, it might look very obvious because we only have one output, but when you have 7, 8, or 20 outputs, you know, this actually will become a common mistake. Okay, and just before we go, let me just mention how would you write down the state machine right here. Of course, I have it ready already. I mean, I have, you know, what I did is I used another example, and now I am just editing this. Okay. By the way, there is nothing wrong with you doing that. Actually, I would recommend that you do that. You edit previously designed files. I mean, if you try to do everything from scratch, it will take you forever to complete. Let me do that. That will be clock reset. I think it's X and C. There you go. Okay, here is the process for the clock in the test bench, and then we have this. I'm not sure if this is gonna work very well. Let me see. 01101. Let's see. So again, you first synthesize just to make sure that you don't have any syntax errors or even warnings. Always pay attention to the warnings. That's a very common mistake the students make. They just jump directly into the simulation without having doing the synthesis part of it. Okay, let's give it a moment. Let's give it a moment and let me show you something, okay, before we finish this lecture. Once you do this, you will be equipped to design any state machines and any digital system, which is the next unit, designing digital systems, which is just a combination of state machines and other blocks. Okay, so it finished. So now, of course, once we run the synthesis, we go here and we see the warnings or the errors, right? Luckily, we didn't get any errors. And the warnings, of course, you just want to watch out for the common warnings, right? I mean, I think I mentioned that already before, in case you have forgotten already. What are the common warnings? So something like multi-driven pin is a common error. That's when you have essentially this is a short. Another common error is inferring a latch. If you see this, I mean, those two, your circuit will not work. Are there more? Another common warning is missing signals in the sensitivity list of the process. Okay. Here we don't have this warning. We don't have a warning of the constraints, obviously, because we don't have any constraints right now, any excessive files right now. Okay, so now we can actually run the simulation. Let's see what we get. Okay, so the simulation run, and this is what we get, right? So we have to, of course, I am going to undock it, and I'm gonna show it to you here. Let's see what we get. Okay, well, as you see, it actually, a sequence was actually detected, because take a look at this, right? Remember, we got 0, 1, 1, 0, 1, and this is the pulse. Okay, 0, 1, 1, 0, 1. Now, what I really recommend you do all the time is to always, when you simulate, because most likely when you have a larger circuit, most likely it will not work, I mean, the way you want it. You have to always be able to view the state, in which state you are at. So to do that, of course, remember, you go to the UUT, and then here you grab the variable state, and then you put it into the wave window, and then you restart the simulation, right? And then you run it for, by default, of course, Vivado only runs for 1 microsecond, but in this case I don't think I need that much. And here we go. Well, as you can see here, you can see the variable, sorry, the signal Y. Right there, right? How when we were at state 2, 3, 4, look how it goes, how it transitions, right? And when we're on state 5, if the input is 1, directly the output becomes 1. Okay? So please, when you do this later for your lab number 6, always look at the variable of the states, sorry, the signal of the states. Okay? Remember, this is just a label, right? This 1, 1 actually is represented by actual bits. Could be that S1 is 0, 0, and S2 is 0, 1. But we don't need to see that, right? We only need to see the labels, because the labels for us is more, they give us more information. Okay? So, and I guess that's all we have for today. Thank you.